Glenn take over the board here and tell us what's hot in cosmology.
Okay, let's see. Okay. Here we go. So now for something completely different. You know, we've been mostly thinking, I think most of us, about viruses and pandemics, but I want to take us away from all that and tell you about cosmology. So, and I'm going to talk about, I'm calling it cosmology on one foot because there's a what's called a midrash, a story about Jewish sages. And the story goes that someone came to a very famous but very strict sage named Shammai and said, Rabbi, I would like to learn all of Jewish law while I stand on one foot. And Shammai said, go away, and slammed the door in his face. And so he went down the street to Shammai's competitor, Rabbi Hillel, who was known as very kind and gentle sort of fellow, and said, Rabbi, I would like to learn about all of Jewish law while I stand on one foot. And Rabbi Hillel said, don't do to others what is hateful to you. Everything else is a commentary. So he managed to teach him all of Jewish law on one foot. And I'm going to try to tell you about a little bit of cosmology while I metaphorically stand on one foot. So that's not me standing on one foot. Maybe that's my daughter. That's also not me standing on one foot. Maybe that's closer to me standing on one foot, trying to tell you about cosmology with a little bit of help from an umbrella. So I want to tell you about two of the things. You know, the title of the talk was advertised as "What's Hot in Cosmology," and I want to tell you about two of the things that cosmologists are thinking about as they sit in their homes, zooming with their students and colleagues, and hopefully also managing to think about cosmology. So I want to tell you about the first thing is called the H0 tension, and the second thing, oh dear, what could dark matter be? So let me start off on the first one, which is to start that the universe is big. I think most of us know that the universe is big. The units in which we measure bigness in the universe are not, we tend not to use meters or kilometers because it's too inconvenient. Instead, we work in units where we use the speed of light, and we talk about how far light can travel in a particular amount of time. So to give you a handy reference, if you look down at your foot, it takes light about a nanosecond to travel from one end, from your heel to your toe. And that means it takes light about just over a second to travel between the Earth and the Moon. And there's this great little sound clip that I'm going to play for you. And if you listen closely, you will hear some people talking, and then you will hear an echo.
That's a pretty outstanding picture here, I tell you. Come on a little bit closer.
So did you hear the echo of "that's a pretty outstanding picture"? It took, it was 2.6 seconds after after you heard it first, and that's the round trip light travel time between the Earth and the Moon, because that was the Apollo astronauts, some Apollo astronauts talking to Houston. So the Moon is about a light second away, and we are about 500 light seconds away from the Sun, which is 8 minutes, and the scale of the solar system is light hours. So we can measure distances in the solar system in units of hours. And how would we go about doing that? Well, we would do things like we could actually, in the solar system, we could bounce radar beams off of planets. We could send satellites to orbit planets and figure out how long it takes the signal from them to get to us. So we can make very direct measurements of the size of things in the solar system on the scale of light hours. Then if we look out on a dark night, maybe even in Cleveland tonight. We'll see. It's kind of unusual. If you went somewhere out in the country, so took a drive and went out in the countryside, you might manage to see a beautiful sky like this. And you would be seeing not billions and billions of stars, but thousands of stars on a dark night, thousands of individual stars. And those stars tend to be within the nearest, within, tens of light years from us. Okay? So, maybe 30 million to 100 million light seconds away. And we can measure the distance to those stars directly by the same technique that you use to figure out, that I would use to figure out how far away this beer, can you see the beer? I have to put the beer in front of me, how far away this beer is from me. I know how to bring that to my mouth and get the lip of the bottle to, in the right place. And that's because I have two eyes and I'm able to look from different directions at the beer bottle. And so when I go to grab the beer bottle, I usually don't miss. And so with those two different views, I'm able to see two eyes, I'm able to see slightly different views. And so I'm able to triangulate on the beer bottle. But we can do the same thing as the Earth goes around the sun. We get two different views of the sky out there. And if we do that, we notice that stars, the nearby stars, tend to move. Well, they move a little bit. The closer a star is, the more it moves as the Earth goes around the sun, because we're looking from a different side of the sun. And that's about 1,000 light seconds across that baseline. And that is good enough to get us a substantial fraction of the size of our galaxy. Okay, so our galaxy, this isn't actually our galaxy. It's really hard to take a picture of the Milky Way galaxy from outside the galaxy because we're inside the galaxy. This is a galaxy that we think looks a lot like ours. It's called NGC 7331. And like the Milky Way, it's about 100,000 light years across. So, and beyond that, we have to use other techniques than parallax to tell how far away things are. What we use are what's called standard candles, typically. So a standard candle just means something whose brightness you know. And so think of we could know exactly when we lit them, exactly how much energy was coming out of them. And then if the candle was close to us, it would appear very bright. If we moved it away, it would appear dimmer. If we moved it away further, it would appear dimmer still. And so by measuring how much light we're actually receiving from the candle, we can tell how far away the candle is. Now, we can use that technique to see distant galaxies and measure how far away they are. And we see that galaxies like the Milky Way are gathered into clusters. We happen to live in a very small cluster called the local group that has only 3 big galaxies about the size of the Milky Way. But typically galaxies will live in clusters that have tens to hundreds of such big galaxies, and they will be those clusters will be millions of light. Many different standard candles. The one that has been particularly useful over the last couple of decades are what are called type 1a supernovae. And type 1a supernovae come about when stars called white dwarfs merge. Now, a white dwarf is what will eventually happen to the sun when it runs out of nuclear fuel to burn. So right now the sun is about 1.5 million kilometers across. And you might wonder, why does the gravity of the sun not pull it together more than that? And that's because the nuclear burning at the center of the sun, the fusing of hydrogen into helium, keeps the sun hot. And that heat causes pressure that counteracts the gravity and keeps the sun big. Well, one day, 3.5 to 4 billion years from now, and at that point, it'll get smaller and smaller until it's only a couple of thousand kilometers across, and it'll won't be burning, and it'll slowly cool. That's called a white dwarf. Well, if you have, it turns out that there's a maximum size for white dwarf. If you make a white dwarf too big, then the forces that are holding the white dwarf up, called electron degeneracy pressure, are insufficient to do so, to resist the gravity, and the white dwarf will begin to collapse. That process typically results in a neutron star forming. A neutron star is an even denser state of matter. It's kind of the difference between an atom and the nucleus of an atom. So instead of a white dwarf, which is about 1,000 kilometers or so across, a neutron star is about 10 to 20 kilometers across. So you're making the same mass a million times denser. That process turns out to result of the collapse of a white dwarf into a neutron star. It turns out to result in an explosion called a supernova, in particular called a type 1a supernova, because there's a number of ways in which stars can blow up and as supernovas. And so this can't resist the gravity anymore. And that means that if a white dwarf accretes, if it adds a little bit of matter, at some point it all of a sudden will collapse and form a supernova. And that makes white dwarfs particularly good standard candles, okay? Because those explosions of the white dwarf tend to be very similar. Now, they're not perfect standard candles. Not every type 1a supernova is exactly the same. However, they appear to be what are called standardizable candles. In other words, there are other properties of the explosion, the supernova, that allow us to tell exactly how bright that explosion was. So if we know how bright the explosion was, and we're able to measure how bright it appears, then we can tell how far away the supernova was. Now, the good thing about type 1a supernova is that they're extremely bright. For a brief period of time, for a few days, the supernova is brighter than the... Yes?
Yeah. What forces bring these two stars together?
Hello?
Yeah.
I thought I heard someone asking a question.
I have a question. What force bring these two stars together?
Gravity. Yeah. So these are, so they're in fact two. Yeah. So these white dwarf, these type 1a supernova are thought to happen actually in two ways: when either an ordinary star is orbiting a white dwarf, or another white dwarf is orbiting a white dwarf, and because of gravity and tidal forces, basically because of the action of gravity on the two stars, the system loses energy slowly, and the stars spiral in, and some of the, if it's a regular star, some of the material falls onto the white dwarf. If it's two white dwarfs, then they start to touch, and one white dwarf starts gaining some matter. So it's all because of gravity. Okay, so this is all a gravitation. But they start out as a binary star. They started as two stars together. A substantial fraction of stars in the universe start out as binary stars. So the good thing about type 1a supernovae is they're so bright that we can see them all the way across the universe out to over 10 billion light years away. So we look out at the universe and we see objects all the way out to over 10 billion light years in distance, and we can measure how far away galaxies are out to these incredible distances. And one of the other thing we can do is we can not only measure how far they are, we can notice that galaxies are moving, and that the universe is getting bigger. So how do we do that? Well, when an object is moving, if it is moving towards us, then the Doppler effect, which is the same thing, the effect that makes a car approaching you sound like it has a high pitch, and a car moving away from you sound like it has a low pitch. Or if you stand beside a train track, you know that if the train is blowing its horn, it'll sound high pitched as it comes towards you, something like. So as it passes you, the pitch goes from high to low. Well, the same thing happens with light. This is how police catch you speeding. They shoot light beams at you, or they shoot radar waves at you, which is a form of light. And if you're moving towards them, then the beam comes back with a shorter wavelength. If you're moving away from them, it comes back with a longer wavelength. And the faster you're moving, the bigger that shift in the wavelength of light. So the police officer is able to tell how fast you're moving by how much the light that they bounce off your car shifts. And in the same way, when we look at distant objects, we're able to tell whether they're moving towards you or away from you. And we've been doing that for over 100 years. When we look at galaxies that are far away, one of the things we notice is that they are all moving away from us. And this was first noticed by a number of people, first kind of understood and put together by really two people. One of them was a fellow named Lemaitre, a Belgian priest, and the other was Edwin Hubble, the person for whom the Hubble Space Telescope is named. And so here we call it Hubble's Law, and Hubble's Law is this observation that the further something is away from you, the faster it will be moving away from you. So there's a linear relation for things that are not terribly far away, meaning within, say the nearest few 100 million light years, you would notice that it's actually linear. Okay, so if something that's twice as far away from you will be moving twice as fast away from you. And our interpretation of that law is that the galaxies are being carried apart from one another as the universe is expanding. This isn't quite the same as an explosion. It's more like raisin dough. So imagine you were trying to make some raisin bread, and you prepared the dough. It was full of raisins, all nicely mixed in, and you left it to rise. Then imagine that you are sitting on one of those raisins. You can choose one of your own, and you can close your eyes and visualize all the other raisins around you. And if you do that, then allow the raisin bread to rise, you look out and you see all the other raisins are getting farther away from you. Okay? So if there was one raisin, let's say you were sitting on this raisin here, and you looked out and saw this raisin over there that was 1 centimeter away, and we allowed the dough to rise for an hour, and it would move to 2 centimeters away, and that means it would have moved 1 centimeter in 1 hour, so it's moving at 1 centimeter per hour. But if you looked at this one over here, it was say 3 centimeters away. It was 3 times as far away, and when the dough rose, it was 6 centimeters away, so it moved 3 centimeters per hour. It was 3 times as far away. It moved 3 times as fast. That's Hubble's law. So in this case, in the case of the universe, the dough is space, the raisins are the galaxies, and really the clusters of galaxies being carried apart by the expansion of space. Now, one thing to know is that because of that expansion, the universe is getting cooler. So expansion of things like gases and plasmas, the things that fill the universe, causes them to cool. And
so when the air expands,
there's actually a little video I wanted to show that I think he's quite a character, and he does a pretty good job of demonstrating this. So I'm going to show that video and let you watch it.
then the air cools. HC. I got a demonstration for you all to try right there at your seats.
Okay, everyone try
Are
this.
you ready?
Get ready.
Everyone have a hand? Put your hand in front of your mouth, and with your mouth open, so when you breathe, so the air doesn't expand, I want you to blow.
Hope everyone's doing this.
Now bring your mouth down really tight so the air expands when it comes out. Notice any difference in temperature? Okay, you want to see that more dramatically? Watch
So
this.
it's much cooler.
Here's some steam here. Huh?
They have a pressure cooker, and he's going to let the steam out of the pressure cooker.
Would I dare to take this glove away? Yeah, easy. Easy thing, no problem. Hot or cold? Begin with a C. It's cool, relatively cool. HC. I'm not going to put it way down at the nozzle. It turns out that that which you are seeing here, gang, is not steam. That which you can't see, that's the steam. But what does that steam do? Begin with the X. Expand. And when it expands, what's it do? Begin with another C. Cool. And there's your evidence right there. Isn't that remarkable?
All right, so the universe is expanding, and so it's cooling. And if it's cooling, then it used to be hotter. And so we look out. So we look out in the universe, and we can look for that light that was emitted when the universe was hotter. So back when the universe was, let's say, so if in the past the universe was hotter, at some point in the past it was as hot as, say, the surface of the sun, right? And if you look at the surface of the sun, don't try this at home. If you look at the surface of the sun, you'll notice that it is glowing, right? So you don't want to do that too long because the light is really bright, and it's really, the photons that are coming from the sun are very energetic. They could come into your eye, and they're going to hurt your eye. And so you might wonder, well, if the universe used to be that hot, why don't we look out and see a really hot universe? Because if I can look out in the universe, I'm looking back in time. I should be able to see back to the time when the universe was hot. What happened after it was hot? Well, so I had a hot universe full of plasma. As the universe expanded, it cooled. In cooling, it became neutral. So when the universe was very hot, the gas inside the universe was ionized. It was so hot that the electrons couldn't attach themselves to the nuclei. They ran around. When the electrons are on their own, they scatter photons really, really well. And so when they do that, the photons, the particles of light, can't travel through the universe, and the universe is opaque. Then as the universe expands, it gets cool enough for the electrons to reattach themselves to the nuclei. At that point, they can't scatter the light, and the light is able to travel through the universe. So if I'm looking out on the at night in the sky, I should be able to look out and see that light that's coming from when the universe was very, very young and very, very hot. And you might have noticed that when we look at it at night, the universe doesn't look like it is hot like the surface of the sun. And that's because as the light is a wave, and as it travels through the universe and the space is expanding, the universe is expanding, it actually stretches the light beams as well. Okay? And this was all anticipated as early as the 1940s, 50s by people like Alpher and Harriman and Gamow. And they said that light would have been stretched, but that if we looked out in the universe, we should be able to see cooler light, the light, that original light that used to be like the surface of the sun, but now it had been stretched, and we should see it as microwaves. And sure enough, in the 1960s, we were able to build antennas like this, use them and look out at the night sky. And two Bell Lab radio astronomers named Penzias and Wilson looked out at the night sky and noticed that it was glowing in every direction. This is in 1965. And they scooped a team from Princeton that was about to build an experiment to look for exactly this. And so when you look out at the night sky, you see in every direction on the night sky a glow from the night sky that's at about 2.7 degrees above absolute zero, that was emitted when the universe was about 3,000 degrees above absolute zero, so comparable to the temperature of the surface of the sun. Now, that's called the cosmic microwave background radiation. And one of the things I could have talked about is the same temperature in every direction within a few millionths of a degree. But I'm not going to talk about that. We'll talk about some other stuff. But this is light from when the universe was about 400,000 years old. And so it's been traveling through the universe since it was 400,000 years old until now, which is about 13.8 billion years later. So we look out at that light, and we look to see if it's exactly the same in every direction. It can't be exactly the same because the universe isn't perfectly smooth. There must be places where the light came from, that it was a little bit denser or a little bit hotter. And so we should be able to see those little variations in the properties of the light. And we did that finally in the 1990s, 30 years later, 25 or 26 years later, using this satellite called the Cosmic Background Explorer satellite that was built by NASA and launched and worked in the early 1990s. And it was able to take this map, which doesn't look like much of a map, what we've done here is taken the sky, which is, you know, a sphere surrounds us, and we've taken it and split it along some, you know, from the North Pole to the South Pole, and unwrapped it and folded it and made a flat map. It doesn't look, as I said, it doesn't look like much of a map because it's the same. But they could look at it more carefully, and the first thing you would notice is that there were small differences between one side up here and another side down here. It was a little cooler down in this bottom part, a little warmer up in this top part. That's the same Doppler effect, top right. That's not very interesting. We already knew we were moving. We knew that the sun was going around the Milky Way, and the Milky Way is moving. But we're able to look at it even more carefully and make this map, where the temperature, the scale here is such that blue areas like this are just a few millionths of a degree cooler than red areas like this or like this. Now that central band is interesting to astronomers, but not to cosmologists. It is the Milky Way galaxy getting in the way of this observation. But these dark blue spots and light reds and red spots up out of the plane, you know, up at the top of the map and the bottom of the map are more interesting. I'm going to show you a more detailed version of this map made by a later satellite, the Wilkinson Microwave Anisotropy Probe in the early 2000s. Here's that version, and we've since improved on it. And we have a map like this. So here's our current best map of the universe when it was 380,000 years old. So why did I spend all this time talking about this map when this doesn't seem to have anything to do with the expansion of the universe? Well, we're able to use two basic techniques now to measure that relationship between how fast things are moving away from us and how distant they are. In other words, to measure the expansion of the universe. We're able to use objects like type 1a supernovas to measure that relationship. And we do that over relatively small distances, like, you know, hundreds of millions of light years. And then we're able to use the cosmic microwave background. We're able to use the physics of the patterns, of the statistics of these patterns in the microwave background to make the same measurements, okay, to measure the expansion of the universe. And when we do this, we find something interesting that's called the Hubble tension. So here I have a graph, and on the vertical axis, I have this H0, this measure of how fast the universe is expanding. And on the bottom, I have the year in which the error bars on the measurements are pretty large. That, you know, here we have, you know, some measurement that the answer is in some units that we don't really care about, 72. But 72 plus or minus about 8. Okay, so somewhere between 64 and 80. Okay? And that was a measurement made with objects, actually not type 1a supernova, but with bright objects. Actually, maybe that was the type 1a supernova one. So all these blue are type 1a supernova measurements. And you notice we start here with this one that's 72 plus or minus 8. And here we get by 2009, where our error bars are smaller. They're only about plus or minus 4 or 5. The value isn't changing very much as time goes on. We're staying within our error bars, so this seems pretty stable. And we get to today. Well, this is 2017, but it's good enough. 2016, and we see that the answer is about 73 plus or minus 2. 73 plus or minus 2 kilometers per second per megaparsec. So that's using these type 1a supernova. And then we go back to 2003 and that Wilkinson microwave anisotropy probe, or WMAP satellite, and it comes out with a measurement that's, pretty much in agreement with that. It's, 72 plus or minus, goes up to 70 plus or minus 5. And time goes on, and the WMAP satellite makes some improved measurements, and then the Planck satellite makes an even more improved measurement, and it's a little bit lower. And you see now that by 2016, we have an answer of 67 plus or minus about 1 kilometer per second. Now, these two numbers are quite different. They differ by about 10%. Now, in cosmology, 40 or 50 years ago, used to be a science in which one argued about factors of 2, but instead we're looking here at 2 measurements that are differing by 10%, but are statistically very, quite far apart. The microwave background measurement is measuring the expansion rate relatively early. It's measuring it's measuring a system that is very far from us, 10 billion light years away, 10. It's a combination of measurements that are anywhere from about 13.8 billion light years away to a couple of billion light years away. Whereas the supernova are measuring things that are closer, only a few hundred million light years away. And these things differ in our theory. And the question is why? And so that is one of the really big mysteries in current cosmology. And there's 2 possibilities. Why do they disagree? It could be that one of them is wrong. Or it could be that there is completely new physics that we have to introduce to explain why the expansion of the universe doesn't agree, that there was a sudden change somewhere in the expansion history of the universe, or that there's something we fundamentally don't understand about one of these measurements or the other. So that's the first thing that I wanted to tell you about, and a good place to stop for some questions.
So Glenn, can you hear me?
Yes.
Is it possible that—
Any questions?
Yes, I'm asking a question.
Yes,
is it
David.
possible that the expansion changed from the early universe to late, that we're accelerating now?
Did you hear that, Glenn?
Should I write it?
Well, so this takes into account the possibility that they're accelerating. Yes, sorry. Yes, I thank David. Did everyone? I think hopefully everyone heard David's question. Yes. So is it possible that the rate of expansion is changing? Yes. So these were both measurements of. So the measurement with the type 1a supernova was a measurement of today's expansion rate. The measurement with the microwave background, even though it was using this measurement of stuff that was from 13.8 billion years ago, the cosmic microwave background, what I'm quoting to you is what that would tell us about today's expansion rate. And so it's giving us 2 different values for how fast the universe is expanding today. So they can't both be right. Okay? So that tells us that either one of the measurements is wrong, or the theory that we're using to extrapolate from when the universe was 13 billion years ago, 400,000 years old, to today is wrong. Or that our understanding of the history of the microwave background and how it was formed is a little bit wrong. So some ingredient here, either one of the measurements or the theory that's going into our understanding of the measurements is wrong. And I'm, you know, there are a number of ways that people are thinking about how to fix this. All of them somewhat, you know, somewhat radical in the sense that they require new forms of energy that we didn't expect to be injected in the universe or something else. So it's really one of our real current puzzles. Okay. Thank you, David. So I'm going to go on to our second mystery. And but this one will take me a little less time to explain, a little less complicated story. So I like to sing this mystery, and it's oh dear, what could dark matter be? Dear, dear, what could dark matter be? Oh dear, what could dark matter be? Tell me and I'll go look there. So first of all, what is dark matter? Well, when we look at galaxies like this is NGC 3949, a galaxy kind of like ours. We expect the more distant parts of the galaxy to move around more slowly. Okay? And I'll try to explain why. So the first thing is we see these galaxies spinning, and we wonder, you know, what is holding them together? Because something better be holding them together, right? If you go to the amusement park and you see some ride like this with the swings going around a central axis, then you will be very reluctant to get on if you notice that the swings are attached by dental floss or by you know some string. Okay? You want them to be attached by some nice strong chains that can pull hard enough to keep the swings going around and not let them fly off into space. So what about a galaxy? What holds a rotating galaxy together? Well, you know, under similar circumstances to what we're in today, you know, 350 years ago or so, Isaac Newton was perhaps sitting under an apple tree and noticed that apples were falling from the tree, and also noticed that the moon seemed to be going around the Earth, and he figured out a law of gravity that connected to the two. And he figured out the inverse square law of gravity. And so Newton's law of universal law of gravitation is remarkable. It tells us how the solar system works, why the more distant planets move more slowly because they're further away from the big source of mass in the solar system, which is the sun. Essentially, nearly all of the mass of the solar system is in the sun. And so the farther away you go, the slower you move around the sun, because if you move faster, you would fly off. So when we look at a galaxy, we could ask, well, what supplies the gravity for the galaxy, which is spinning? It could be the stars. And this is an infrared image from the Spitzer Space Telescope that shows hundreds of thousands of stars in the Milky Way galaxy. It also shows, like we see very clearly in this nebula called the Elephant Trunk Nebula, which is a couple thousand light years away, gas and dust. And so the galaxy is visibly made of stars and gas and dust, and we would think that they would supply gravity to keep the galaxy together and stop it from flying apart. And the problem is, it isn't enough. When we add up all of the stars and gas and dust and do a very careful census, as we are required to do, we find that spinning galaxies should fly apart. Okay? And the person who really taught us that was Vera Rubin. What she did is she measured the rotation curves of all sorts of galaxies. On the bright part of the galaxy, and you looked at tracers that were, outside the bright part of the galaxy, that speed of rotation became approximately constant. So that would be as though Saturn was moving just as fast as Jupiter, and Uranus was moving just as fast as Saturn, and Neptune was moving just as fast as Uranus. And you say, how can that be? They're getting farther and farther from the mass of the solar system. In the same way, the things she was measuring were farther and farther from what appeared to be the mass of the galaxy, and yet they were going around the galaxy with about the same speed. Here are a bunch of different galaxies, and you see all of them have these what are called flat rotation curves. This had been noticed actually before in the 1930s by Fritz Zwicky, who is a Hungarian astronomer at Caltech. He noticed it not in galaxies, but in clusters of galaxies, that clusters of galaxies should have flown apart and didn't. But apparently he was a rather unlikable fellow or dislikable fellow. No one paid attention to him, and no one noticed until Vera Rubin's work in the 1970s. And these days we wonder why she didn't win the Nobel Prize for that. And so there are two possible solutions to why galaxies are holding together and why clusters of galaxies are holding together. One is that Newton and Einstein were, and I don't know how to spell, has two E's, of course, were wrong about gravity, that actually the gravitational force doesn't fall off as 1/r² as you get that far away from the galaxy. There's extra gravity out there, and we just, we have to change our law of gravity. And the other is that there's actually missing matter. And I'm going to focus on that second explanation. The first explanation is something that people have been trying to make work. It's been challenging. And so we don't know that it's the wrong explanation. It might be the right explanation, but so far we've failed to come up with compelling theories that, that make it work. So if there's missing matter that we just don't see, we call it dark matter because we don't see it. And the question then is, what is that dark matter? Well, could it be stars? Well, if it's stars, it's not very dark. So stars do not make dark matter. But stars eventually run out of nuclear fuel and become things like white dwarfs and neutron stars and black holes. And maybe those would be good dark matter. And in fact, they would be wonderful dark matter. They could be out there, very hard to see, and hold the galaxy together, provide lots of extra gravity to keep the galaxy together. But the problem is that stellar death is messy. It results in things like supernova. Right? And not only that, when the supernova happen, when the stars die, they tend to throw off most of their matter and leave just a little bit behind. And so it's we don't know how to make all those dead stars so that they could be the dark matter. So not dead stars. Okay? So in fact, stars, dead stars, planets, gas, dust, none of them work as dark matter because we now know that the dark matter seems to have had to be in place before the universe was about a second old in order to explain the properties of the microwave background. So none of these things make very good dark matter. And neither do, people will say, well, what about those giant black holes that sit at the centers of galaxies? Yes, those would also make wonderful dark matter, except they're not big enough and there's not enough of them. And then, well, what about elementary particles like neutrons? Neutrons would make wonderful dark matter, except they decay. In fact, there's no known elementary particle that would make good dark matter. And so particle physicists who have been the most interested in dark matter say, well, if it's not any known elementary particle, and if it's none of these objects that we know exist, we better invent some new objects that could be dark matter. So they invented many things, but the two most popular, one is called WIMPs, or for weakly interacting massive particles. And these are objects, these are elementary particles that are typically thought to be 10 to 300 times the mass of the proton. Particles called neutrinos, they're made in nuclear reactions. So for example, nuclear reactors emit them, nuclear bombs emit them, the sun emits them, and we've measured them from well, at least from nuclear reactors and from the sun, and also from supernova. And though they are able to travel through light years of ordinary material. So neutrinos are made in the center of the sun and travel all the way through the sun without bouncing around in the sun at all because they interact so weakly. So we can imagine other particles that, unlike neutrinos, which are terribly light, instead are more massive than ordinary protons and neutrons, and have similar weak interactions. And those would make wonderful dark matter. And particle physicists have also imagined heavier than protons are extremely, extremely light, but kind of like the photons inside of lasers that come out of lasers, they gather together into a coherent state of what's called a Bose condensate, kind of. And they also would be wonderful dark matter. And each of these was invented, and the reason particle physicists were excited about them is because they weren't invented in order to be dark matter. They were invented in order to explain possible problems with the standard model of particle physics. And so people have gone out over the last 50 years and built WIMP detectors. And here is a picture of a WIMP detector that was actually built in the basement of, much of it in the basement of Rockefeller, of the Rockefeller building on campus. So right here, Tom Schutt was a professor at Case Western until a few years ago. When he and Dan Akrib, who many of you know as well, were recruited away to build an even bigger detector like this for the Department of Energy. Okay? So this is inside of here was a large vat of liquid xenon, and buried a mile underground in an old mine. So that ordinary cosmic rays couldn't get down to it, but dark matter could come through the Earth, hit the liquid xenon, and we would see the dark matter particles activate the detector. People have also built axion detectors. Here's a picture. Here's a particular axion detector that looks for axions turning into light, which they could do in principle if you put a magnetic field there. And so this is called the axion dark matter experiment, which looks for photons for axions turning into photons in the presence of magnetic field. Here's another one of those, very similar, pointed at the sun, looking for axions coming out of the sun, turning into photons. And here is a dark matter, what was hoped to be a dark matter factory, a WIMP factory. This is a picture of the Large Hadron Collider, which is the largest machine ever built. It sits under the countryside near Geneva. It's 27 kilometers around and accelerates protons up to energies thousands of times their rest mass, and then smashes them together at these places where there are labels like CMS and Atlas. Here is one of the detectors that you put at the places where they smash the protons into one another. This is actually the Atlas detector before it was completely built. You can see here a person for scale. Here's the CMS detector, or compact muon solenoid detector. And in both of those cases, the hope was that one would produce these dark matter particles. Now, you notice that no one has announced the discovery of either the axion or the WIMP. And so far we haven't seen WIMP dark matter or axion dark matter. And that was especially the WIMP dark matter was kind of a huge disappointment. People really expected that we would discover something called supersymmetry, which was a theory that predicted that there would be a new stable particle called the lightest supersymmetric particle, or lightest supersymmetric partner, a stable particle with mass tens to hundreds of times the mass of the proton, which would make wonderful dark matter. And that would then also be seen in detectors like that liquid xenon detector buried deep in the mine under South Dakota. And so that disappointment from not having seen WIMPs in particular, or also axions, has excited cosmologists to go back and think about all sorts of other possible dark matter particles. One of the ones that, and some of these are things that people have been thinking about for a long time, really since we realized that there was dark matter. So one of them is primordial black holes. So black holes made not from dying stars, but back in the early history of the universe, when the universe was less than a second old, we can imagine processes that might make black holes. The masses of these black holes wouldn't have to do anything with the mass of a star because they're not formed from dying stars. And so they could be any mass, really. We believe that black holes actually evaporate. So black holes are able to emit energy, and the lighter they are, the better they emit energy. And so it turns out that if a black hole had a mass less than about 10 to the 15 grams, then it would have evaporated away already in the history of the universe. And so it wouldn't be very good dark matter. So they would have to be heavier than 10 to the 15 grams. And they could be anything above that. We have lots of various ways that we can try to look for them. Okay? And one of the leading ways is to look for the gravitational lensing that they would cause. You can imagine if you have a big black hole floating around in the galaxy, that light traveling by it would be bent by the black hole. That actually would cause something behind it to get magnified, to appear brighter. We can look for that, and we haven't seen that. And so we know that if the dark matter is made of primordial black holes, they have to be lighter than the Earth. So there's this whole range between about 10 to the 15 grams and the mass of the Earth at which people have been looking for primordial black holes. The one that I happen to be particularly interested in is that, in fact, it's chunks of nuclear matter, very much like neutron stars or like lead nuclei, but instead of just being made of protons and neutrons, which are made of up and down quarks, two of the types of quarks, these also contain the third quark called the strange quark, and so it's called strange nuclear matter. We don't know whether strange nuclear matter is stable. If you take nuclei much bigger than lead, they start to fall apart. Right? You can't have huge nuclei. They undergo fission, they break apart. But it's not known whether strange nuclear matter that contains strange particles, all sorts of strange ways of trying to look for strange nuclear matter. That I'm not going to tell you about, because the point was to tell you about the interesting things that people are thinking about. And so primordial black holes and strange nuclear matter, dark matter, are two of them. And then there's all sorts of much weirder stuff whose masses range from 10 to the minus 50 grams up to about the mass of the Earth. So far, we haven't found any of it. And so those are the things we're thinking about. We're thinking about what could the dark matter be. So, oh dear, what could dark matter be, dear, dear? What could dark matter be? Oh dear, what could dark matter be? Tell me and I'll go look there. And now I'm happy to take some questions.
Glenn?
Andrew Kabir.
Glenn, can you hear me?
Annie, yes.
Yeah, can you tell me in a sort of typical galaxy, how much additional mass is needed to solve the rotational problem?
Oh, you need the total mass to be about 10 times what we see.
A huge amount.
Yes, a huge amount.
Okay.
Yeah, so at our distance from the center of the galaxy, we're about 2/3 of the way out in the visible part of the galaxy. At our distance, the density of dark matter is about the density of ordinary matter. Okay? But go beyond that, and the density of dark matter is much larger than the density of ordinary matter because there's less and less ordinary matter. And the galaxy is much bigger than the visible part that we see. So the part we see is about 100,000 light years across. but it appears that dark galaxies are several 100,000 light years across in the dark matter. They almost merge into the next galaxy.
Then, is there any way to estimate the distribution of dark matter? How it could be, I don't know. You can assign it some mass or some other property.
So that's a great question, David. So recently, there's been something called the Gaia mission, and the Gaia mission is a European Space Agency mission that is measuring the positions and velocities of billions of stars in the Milky Way and nearby galaxies, and so it's making a dynamical map of the kinetics of our galaxy out to a significant fraction of our galaxy. And so the hope is to be able to use that to understand the galactic potential, the gravitational potential of the galaxy. And as well, there are all sorts of structures which are things like globular clusters, clusters of stars that were all made at the same time in the same place, that as they've traveled around the galaxy have gotten stretched out into long streams. Also, galaxies, small galaxies that fell into the Milky Way that have gotten stretched out into long streams. And by studying those streams and studying the kinetics of the stars, there's hope to be able to map out the gravitational potential of the galaxy, which essentially amounts to making a map of the distribution of the dark matter. Now that's a map that is in which the information is about the large scale distribution. I mean, on the scale of hundreds of light years or thousands of light years. It doesn't tell us how big the particles of dark matter are. And so that's a bigger challenge to try to figure out, can we figure out how big dark matter particles are? Do they have masses of a proton mass, or do they have masses of an Earth mass? That's a pretty big range, or 10 to the minus 50 grams. So we're uncertain by 70 orders of magnitude what the actual mass of the dark matter particles is. So David's frozen for me. I don't know if other people are frozen or if I'm frozen.
I can hear you.
No,
Oh, good.
that's fine. You gave good answer. My question was about large scale, of course, right?
Yeah. So there's a good chance that we will get a good large scale map of our galaxy. We get reasonably good large scale maps of clusters of galaxies by looking at the gravitational lensing of objects behind them. And we're going to improve in that as well, mostly by looking at, so we have clusters of galaxies, and we will look at all the galaxies behind them and how they get distorted by the gravity of the cluster. And we're launching a satellite. We have a survey called the LSST, that actually it's now called the Vera Rubin Observatory, and that will map many, many such clusters of galaxies. And also we're going to launch hopefully a satellite called WFIRST, and those will make maps of the galaxies around clusters to look at how they're distorted, and that will allow us to reconstruct the shapes of clusters of galaxies, or the dark matter profiles of clusters of galaxies. But still won't tell us what the dark matter is.
So we hear about physics being split into, experimentalists and theorists. And you've talked about several ways of combining that. If somebody were wanting to go into one of these areas today and they were interested in one of these questions you've talked about, I should say, if you were to do it, if you were 17 years old, what would you do?
Well, I can tell you what my son Nathaniel's doing, who's going into this. So, which I think is a pretty reasonable thing, is he's actually gotten interested in studying this Gaia data, which is looking at the dynamics of objects within the Milky Way as tracers of the dark matter. I think that's a very interesting thing. I think, you know, it's actually a fascinating time for dark matter studies in that it's shifted entirely. 10 years ago, you really wanted to be working on one of these WIMP detectors, like the Large Underground Xenon experiment that was built here at Case and was in the underground mine in South Dakota, or an Axion experiment maybe. Now there are so many different opportunities, there's so many different candidates, and we don't really know which one is the right one, that probably the best thing to do is to join one of those and hope you've joined the right one. I think, you know, from my own taste, some of them are more attractive than others, but my taste isn't necessarily everyone's taste.
Yeah, Glenn, this is Vincent. Can you hear me?
Yes, go ahead, Vincent.
Yeah. You talk about hot topics, and this is maybe more particle physics than cosmology. People talk a lot about this quantum entanglement and how this relates to Higgs boson and so forth. What's the meaning of all this for cosmology?
That's a great question. And I'm not sure I would want to give a good answer off the cuff, because my answer off the cuff would be not much. But there are certainly people thinking about whether one can detect quantum entanglement in the microwave background radiation, or in the pattern, in particular, in the pattern of those hot and cold spots that I showed you on the sky in the microwave background. There's some possibility that one could detect the quantum entanglement that lasted from when the universe was nearly 0 seconds old to when the universe was, 400,000 years old. That's one answer. I think there are other answers having to do with the current accelerated expansion of the universe, but I'm certainly not an expert on those, and I wouldn't want to give you an off-the-cuff answer.
So do people still try to reconcile gravitation theory with quantum theory of?
Oh, absolutely. Yeah, absolutely. So there's still a whole community of people who work on that interface between gravity and quantum mechanics. Many of them are thinking about the properties of black holes. Yeah, I would say we still don't know definitively what the answer is, but there's certainly lots of people trying to think about it. And we might want to try to get Kurt Hinterbichler to give us a talk about that, perhaps, or we'll think about getting someone from somewhere else who thinks about it more directly.
Yeah, thanks.
Sure.
So I see that Dustin Tyler has joined us. Dustin, could you say for a second what your talks are going to be on in a couple weeks here?
Sure. Actually, I'm sorry. It's been crazy times, as we all have, I'm sure. So I'm sorry I'm late. I want to see if I catch the end of this. But yeah, I'd be happy to tell you what I'm doing.
Yeah, that'd be great. Can you put your camera on, or?
Oh, Lord, you don't want that. Yeah, hold on a second.
All right, whatever you prefer.
We'd much rather have a picture of you when you were 15.
Well, that's our faculty picture, isn't it? When it's much longer ago. Those are never accurate. Yeah, so basically, there's 2 weeks, right? So the past and the future is kind of, or past, present, future. What I'll spend the first one, I think, on the 17th it is, or whatever that 14th, I guess.
14th, yeah.
That is 2 weeks. I'll talk about what we've been doing in terms of restoration for sensory. I'll start with a little bit of the background of connecting to the nervous system, the work I do to actually communicate directly to the brain and to the peripheral nerves. And then talk a lot about what we've learned about restoring the sense of touch to people who've lost their hand and what that means. And then from there, we've actually started to expand that into not so much just restoration of sensation and prosthetics, but it has a much broader application to really connecting man and machine in a way we've never been able to do before. And so thinking about how the transformation of the symbiotic relationship, if you will, the direct connection between human and technology could potentially transform many, many different things. And so this is the idea of a symbiotic embodied relationship between machine and technology and humans. So that's the gist of what it is. If that doesn't make sense, I can clarify, I hope.
Well,
Looking forward to that. That
yeah,
sounds great.
I hope people will come and hear the discussion or your talk, and then the discussion will clarify anything that they need. Yeah.
Yeah, actually, if you don't mind, I mean, I can share we've been thinking about this COVID issue and where, this idea of human machine robotics and all that might merge in an area that would help with that. And I can share a link if somebody wants to take a look at a kind of a web page that we're starting to put up around that, if it's of interest, that can kind of maybe seed the discussion.
Yeah, sure. Put it in the chat.
Yep, just put it up there now.
Wonderful. All right. Well, we're all looking forward to that. Does anybody else have any last questions for Glenn? I think we're way over time. So. Glenn, any last words?
My last word is take a few moments to think about something other than COVID, at least once in a while. It helps to keep us all sane.
Very good. All right. Well, we'll see you guys.
See everybody, and look forward to
Thursdays and Saturdays.
Yeah.
Thank you.
All right. Thanks, Glenn.
Thank you.
Thanks, everybody.
Thank you.
Okay. Bye.
Bye.